for the bar work, the approximation that leads to the most correct answer for the area under a function is MRAM. And so if you recall, the MRAM is where we use the midpoint of the rectangular region to draw the top of the rectangle. So if we have a function that looks something like, let's just take something that looks a little quadratic, and we start drawing rectangles here. If we're taking our intervals here, then as we go up here, we look at the middle of that interval and we draw the top of our rectangle there. So here's our next interval, and the middle is about here. So we take that function value and draw the top of our rectangle, and in the next region, the middle of the function there. So there's the top of our next rectangle, and that allows us to then kind of split the difference between what is underneath the function and what is outside the function. So it allows us to split the difference there between area inside and gaps under the function and area outside the function. And so today we're going to be taking that idea of a Riemann sum, and we're going to be using the midpoint specifically, since it does give us the closest answer, to extend that into what a definite integral is. When we're talking about taking a Riemann sum, and you can do this with any of the ones, you can use left, right, or middle, but middle is the most accurate. The notation then for using an MRAM, so to speak, to find the area is this top notation here. So if we look at this, each one of these a sub 1, a sub 2 are areas of rectangles. So what we're saying is they were talking about the area. The first one would be the area of the first rectangle, the second one would be the area of the second rectangle, and we'll add all those rectangles up until the last rectangle here, just like you've been doing all last week, and that should give us an approximation of the area underneath the function. So here's my approximation total of the area. And so just to familiarize you with summation notation then, if we look at writing it as a summation, that means using the sigma symbol. And so if we kind of look at this notation here, so here would be the area, the total sum you come up with. This is the summation notation. So k equals 1 is that first rectangle. N is that last rectangle. And then if you notice this whole expression here, that is your A1 or your A2 or your A3. In other words, that is how we're calculating each area of the rectangle. So we have the value of the function, and that's the height of your rectangle, and then the delta x, which is the width. Remember, delta means change in x, delta means change in, so this is change in x, so this is the width of the rectangle. And so together those things get us our area. So I have a relatively complicated function here, but I use this just because I want to start extending our discussion about what happens when the function goes below the x-axis. And so I put this function into a program that does Riemann sums. That's in an internet-based program, and the website is down here if you would like to actually create these graphs yourself. You can plug in any function. So we plug in the function here, and so in this case, if we look at this, I did this function from, if you notice the endpoints here, this would be my lower bound. If I were to do this in the Riemann program, this would be my upper bound. This would be the MRAM. That's what the position means. And I am using 18 partitions. And so when I did that with this function, if you notice the summation notation up here, if you notice that summation notation right here, we have, here's again our first rectangle. This represents our last rectangle. Remember, I had 18 partitions. The long expression here, this polynomial to the 5th power, is our f of x. And so that represents the height of our rectangle. And then the delta x here is our width of our rectangle. And so that's what it would look like from a function standpoint. So when I used a middle Riemann sum with 18 partitions here, I found that the area, which is noted right here, the area is 4.08111 square units. Okay, and so I wanted to talk a little bit about what it means to go above and below the x-axis, because we're going to have to start kind of considering that. The definition of calculating a sum in calculus really means that if we have area underneath the axis, that actually counts as a negative area. So if we look down here, this section here is negative area. So that will count as a negative. If we would just do that domain from -1 to about -1/2, we get a negative value for the area in our Riemann program. Same with this. This is negative area as well. And it's negative area because the height is negative. So we have some negative area, and that is because the height, the f of x, so to speak, is negative. And then we have some positive area here. We've got some positive area here, so that would be positive area, and this would be positive area here. And so if we add up all our positive area and our negative area together, so here's our positive area, that's where our function is greater than 0, is positive, or the height is positive. And so this total then, this 4.08111 is in consideration of the fact that we have some area, positive area, and some negative area, so it's really kind of the net area. So at this point, we really want to relate this to what it means to have a definite integral. Okay, a definite integral is a limit process. So we want to tie this into this, and we're going to deal with this concept for the remainder of the school year, really. But this idea of a definite integral, and if we go back to what we had before here, so this is just that previous picture. We have a Riemann sum, and we have this net area, or I'm just going to refer to it as the area under the, and we keep saying under the curve, but really it's between f of x and the x-axis. That's technically what we're talking about here. So sometimes it's you know, if it's underneath the x-axis, is we've got that negative area. But we kind of generally call it the area under the curve, but technically we mean trapping that curve between trapping that area between the function and the x-axis. So here's that area that we started with, that 4.0811, when we had 18 partitions. And so this next picture here now is looking at what happens when we bump up our partitions to 36. So if you notice, the gaps get smaller. And the purple Riemann sum rectangles start to more closely follow the function. And so this area becomes more precise or more accurate. And so we now have an area of 4.0578, and then we're going to increase the number of rectangles again. And so now we're looking at the number of rectangles being 80. So I've got 80 rectangles drawn in here, and our gaps are continually getting smaller here. So those rectangles are even more closely representing the real area. So if you notice, it's 4.05158. So if we notice, we're starting to approach a limit in the value of that area there. So we went from 4.0811 to 4.0578 to 4.05158. So we're approaching a limit here. And so that's what we mean then by continually reducing the width of those rectangles. Or another way to say that is continually incorporating more and more rectangles. So if we notice here, we're going to put infinitely many rectangles in here. And when we do that, when we put infinitely many rectangles, then there are no gaps, or they are so small that they're infinitesimal. And the area, the limit of the area, the limit as those numbers of rectangles approach infinitely many, the area then starts to go to exactly 4.05. So you can see how it's continually getting closer and closer to that value. So what we say then is that we define the integral to be just that. We define it to be that limit. As we make infinitely many rectangles. And so when we take infinitely many rectangles, what we do then is, obviously the rectangles have to be skinnier and skinnier until their width really is approaching 0. And so then the notation for the area between the curve and the x-axis becomes this notation here, where we just look at the upper and the lower bounds here. So this is our lower bound, so our -1 from that function above, and this is our upper bound. And then if you notice, we still have f of x times dx, and so we still have our function here. So our function here is our height. So that's our height of those rectangles that were once there. And the dx, this used to be the delta x. So this is the differential now. And so the idea is that as we get more and more rectangles, they get skinnier, which means their width is approaching 0, and so that width then is infinitesimally small, and so we give it the differential expression dx when we get to infinitesimally small width. And so that brings us to the area of the definition of the area under the curve. And so this is the notation then we associate with taking the limit of that Riemann sum. So using our integration capabilities on our calculator, either the Riemann sum program that we loaded onto the program calculator, or we actually have an fint button, like we had a derivative button also under the math menu. Let's just take a look at the significance of the area between the function and the axis. So when we talk about the significance here, all I'm really saying is that let's kind of look at the phenomenon of having positive and negative area and what that means in terms of getting answers for integration. And so, as I mentioned a little earlier, anything that is below the x-axis is negative area, according to the definition of the integral, and according to the definition of the Riemann sum, because we have our negative height of our rectangle here. So this would be a negative area here. This would also be a negative area. This would be a positive area, and this would be a positive area. So if we look at this just conceptually, we could notice things like, well, there is more positive area, and then there is negative area. Which means if we would integrate from -1 to 2 this function, we should get a positive answer. That should be positive, and in fact we saw on the last page it was 4.05, and that's a positive value. So let's take a look at integrating just a piece of that function. So we're going to take a look at integrating just this piece right here. Just this piece right here from -1 to -0.5. And so when I did that using the Riemann sum program that we have in our calculator, if you notice, I integrated, this is my lower bound, my smaller number. This is my upper bound. I would have to stick that long function into f of x, and then I did the option 6 to get the integral, and if you notice, we have negative area. Okay, so what the Riemann sum program does, and also what the integration process does, is it says, okay, my function's negative, I must have a negative height there, and when I do my height times my width calculation, going back to the beginning of this lecture, when I take my height times my width and I put in a negative value for my height, then my whole area becomes negative. So, and that's exactly what the integration process does. It takes into consideration that we can have negative functions, which in essence means negative heights. So, in geometry, we were always calculating the area of things. And so, in geometry, we don't really talk about this phenomenon of negative height. So if we were to be asked what the area under the curve is from -1 to 0.5, we would still, the physical area is a positive concept. So when we talk about finding the area, if you notice, we stick a negative sign out in front so that we end up with a positive answer overall. So if I want to strictly find the area from a geometric sense, I have to realize that I have a function that is less than 0. I have a function that is negative in that domain from -1 to -0.5. So I have to put a minus sign out front there. So and so this is where we kind of talk about this phenomenon of when we integrate, if we're integrating in a domain or in a location along the x-axis, that where the function might be less than 0 at times, then that integral is saying when the function's bigger than 0, then we're going to have positive area, and when the function is less than 0, we're going to have negative area, and we're going to add up all those positives and negatives to get our net area. So let's take a look at then a function sine of x, where you're very familiar with sine of x, so we should be able to look at this function and kind of hopefully solidify what positive and negative, having positive and negative area is. So here's sine of x. So here's the sine of x. And as it's indicated right here, this is the sine of x, and I've graphed it from 0 to 2 pi, and so we get something that looks very familiar to you. And so what I did here is I calculated the area of sine of x from 0 to pi. So starting at 0, going to pi. And so when I set up this, I can do this 2 ways. I can go into my Riemann program that we have on our calculators, and then do an option 6. So really the partitions don't matter, to find the integral. Or the one thing we haven't talked about is you can actually, under your math key, and this is where we found the n deriv that we were using in chapter 4. There's under the math key, there's an fint option. I think it's option 9, and here's the notation for putting fint into the math function capability. But either way, if you notice, we come up with an area of 2. Either way, any way we do it. So we know the area here for that top portion equals 2. So that's that right there. So you might guess then what happens if we, instead of going from 0 to pi, let's kind of switch this up a little bit. Let's take sine of x from pi to 2 pi. So we're looking at the part now that is beneath the x-axis. So if we look at this part here, that area is -2 because that part of the function is beneath the x-axis. So and so all those rectangles have negative height. So this area is -2. This area is +2. If we would integrate all the way from 0 to 2 pi and include both the upper and the lower portions of the function, and that's what we do here, you can see that when we go from 0 to 2 pi, we get an area of 0. We get that canceling occurring. So there's 2 things we could say. We could ask if we integrate the function from 0 to 2 pi, our value should be 0, because we're being asked to integrate. And being asked to integrate means being asked to find that net area. But they could also say, they could also ask a question, what is the area between sine of x and the x-axis. And so if they're looking for a physical quantity, then that answer would be 2 plus 2, which equals 4. And so because we're talking about a geometric application. So the last thing I want to talk about today is using integration to numerically determine the area of a region. Using what we know just from our area concept to find the numeric answer. And so in order to do that, I wanted to look at a constant function. So we know that f of x equals 3 here is a horizontal line. And we've talked about this before at y equals 3. And so and when we're talking about doing an LRAM or an MRAM or an RRAM, doesn't matter, because we're going to be able to fill the area exactly. And so that being the case, we know that, you know, if we take the Riemann sum of this function from 0 to 2, it's just like calculating the area of a rectangle. So writing this integral then for this specific function, we'd say, well, we're going to do a lower bound of 0 and an upper bound of 2. Those are our values on the x-axis. Our function is the value 3 dx. And so we know that since we have a constant function here, that this makes a rectangle whose on the graph, and the rectangle whose height is f of x, so in this case 3, and whose width is the upper bound minus the lower bound. So we could say like b minus a. So in this case, his width is 2 for us. So we know the area then is 3 times 2, which is 6. So we don't really need to know any more about this notation other than the fact that this notation sets up our height and our width of our rectangle. So so for constant functions, then we can just look at that and say, well, in this notation, this means our height, and the difference of these two values, the upper bound and the lower bound, so the difference of those two values is going to give us our width. And so from there we can do our geometry as necessary. So here's a little bit of an application trying to put two concepts together here. We know that from 0 to pi, this area equals 2. So let's find the area under this function, f of x equals 3 plus sine x, without using any technology. So if we look at this, we can divide this into two regions. And so this upper region looks like sine of x. So we know here that the area equals 2 because we're going from 0 to pi. And this lower region is a rectangle. It's a constant function, and the function starts up here at a value of 3. So we know we have a rectangle with a height equal to 3 and a width equal to the upper bound minus the lower bound, which is going to be pi minus 0. So the width is pi. So the area here is 3 pi. So the total area then without doing any integration type process, just looking at this from the definition of the areas that we have, is 2 plus 3 times pi. So you can go ahead and use one of your calculator programs to verify that answer. So at this point, we have gone through the major concepts of what the integration definition means, and how to apply that using the area model that we've been working with for the last week. So you can go ahead and open up your WebAssign and work on the WebAssign for section 5.2, day 1. And then if you could finish up any 5.1 and 5.5 that you need to. So just a reminder that if you did not get 100% on this, so if you got less than 100% on Blackboard quiz, to finish up 5.1, and then 5.5, I would expect this to be finished at least 100% here. So finish that WebAssign.